Hello everyone. Previously, we have discussed about radioactive decay. What is alpha decay? There are three types, that is alpha decay, beta decay and gamma decay. We have already studied about alpha decay. In today's video, we are gonna see what is beta decay. Radioactivity was discovered by Henry Becquerel by accident. He wrapped a sample of uranium compound in black paper and put it in the drawer that contained photographic plates. On examining these plates later, he found that they had already been exposed. This phenomena was termed as radioactive decay. Beta decay is a type of radioactive decay in which a proton is transformed into a neutron or vice versa inside the nucleus of a radioactive sample. Processes like this and alpha decay allow the nucleus of the radioactive sample to get as close as possible to the optimum neutron-proton ratio. While doing so, the nucleus emits a beta particle which can either be an electron or positron. Remember that there either a proton can turn to a neutron or neutron to a proton. Electron and the positron are generated to obey the law of conservation of charge. The beta decay occurs via the weak interaction. There are two types of beta decay, namely beta minus and beta plus. This is an example of beta decay. Beta minus decay. In beta minus, a neutron is transformed to yield a proton, causing an increase in the atomic number of the atom. The neutron is neutral, but the proton is positive. To maintain conservation of charge, the nucleus in the process also produces an electron and an antineutrino. Antineutrino is the antimatter counterpart of neutrino. Both of these are neutral particles with little mass. They interact with matter very weakly and can even pass through the entire Earth without being disturbed. In a beta minus decay, the change in atomic configuration is given by a parent will give rise to a daughter plus an electron and an antineutrino. Beta plus decay. In beta plus decay, the proton disintegrates to yield a neutron, causing a decrease in the atomic number of radioactive sample. The nucleus experiences a loss of proton but gains a neutron. Again, conservation of charge is important. The beta plus decay, in order to obey the conservation law, also yields a positron and a neutrino. A positron is the antimatter equivalent of an electron. The same in all aspects except that a positron has a positive charge. A neutrino's behavior is the same as the antineutrinos. Expressed in the equation, it is given by beta plus decay can happen only if the daughter nucleus is more stable than the mother nucleus. This difference goes into the conservation of a proton into a neutron, a positron and a neutrino. There is no increase in mass number because a proton and a neutron have the same mass. Health effects of beta particles. Sufficient intensity of beta radiation can cause burns, If beta emitting radionuclides are inhaled or ingested, they can damage the internal cell and organs. Some uses of beta particles. The applications of beta particles include treatment eye and bind cancer, used in phosphorescent lighting, typically for emergency lighting as it requires no power, used as thickness detectors for the quality control of thin materials such as paper. What is gamma decay? Gamma decay is the emission of electromagnetic radiation of an extremely high frequency, that is very high energy, giving out excess energy in order to stabilize the unstable nucleus. You must be quite familiar with various energy levels in an atom. The nucleus too has its own energy levels. Gamma decay is the nucleus way of dropping from a higher energy level to a lower energy level through the emission of high energy photons. The energy level transition energies in the atom are in the order of megaelectronvolt. Therefore, the gamma ray emitted is also of a very high energy of the order of megaelectronvolt, just like X-ray. The gamma rays emitted can be differentiated from X-rays only by the fact that gamma rays come from the nucleus. Due to their high energy, they are extremely penetrating and thereby dangerous to the biological life forms. Here we will speak a little further about distinction between an X-ray and a gamma ray. X-ray are emitted by electrons, either in orbits or in outside application like particle accelerators, synchrotrons, radiation, etc. While gamma rays are emitted by the nucleus, particle decay or annihilation reactions. Unlike alpha decay and beta decay, the parent nucleus does not undergo any physical change in the process. Daughter and parent nuclei are the same. Most of the time, gamma decay occurs after the radioactive nuclei have undergone an alpha or a beta decay. The alpha and beta decay leaves the daughter nuclei in an excited state. From the excited state, the daughter nuclei can get back to the ground state by emitting one or more high energy gamma rays. The image here shows the path taken by cobalt-60 to move from an excited to a non-excited state. The beta decay can leave at either one of the two energy levels. The percentages mentioned next to the beta symbol is the probability of the nuclei choosing either of the two paths. Beta decay followed by a gamma decay. This is the gamma ray equation. Sources of gamma ray. Sources of gamma rays other than radioactive decay include terrestrial thunderstorms and lightning. From celestial bodies such as pulsars, quasars, distant galaxies, gamma rays burst in space and collapse of a star into a black hole known as hypernova or superluminous supernova. Hypernovae events results in bursts of long-duration gamma-ray emissions. These emissions produce a total energy output of about 10 raised to 44 joules, as much energy as a sun will produce in the entire lifetime, in a span of 20 to 40 seconds only. Gamma rays cause damage on a cellular level, and due to their penetrating nature, they can diffuse this damage through the entire body. However, gamma rays are less ionizing than alpha or beta. Hence, the severity is lesser but penetration is more. Applications of gamma rays. Some of the most energetic phenomena in the universe occurs through gamma rays. We cannot witness these events without a gamma ray detector. To address this, scientists have created a satellite called Fermi Gamma Ray Space Telescope that provides an unparalleled view of the universe. Gamma ray sensors are also used in the food packing and chemical industry to measure density, thickness, and composition. Gamma rays are used to treat certain types of cancer where the high energy gamma beams are irradiated on the cancerous cell to kill them. Nuclear energy. What is nuclear energy? Nuclear energy is the energy in the core of an atom. Where an atom is a tiny particle that constitutes every matter in the universe. Normally, the mass of an atom is concentrated at the center of the nucleus. Neutrons and protons are the two subatomic particles that comprehend the nucleus. There is an excessive amount of energy in the bonds that binds the atoms together. Nuclear energy is discharged by nuclear reactions, either by fission or fusion. In nuclear fusion, atoms combine together to form a larger atom, whereas in a fission, the division of atom takes place to form smaller atoms by releasing energy. Nuclear power plants produce energy using nuclear fission. Sun produces energy using mechanism of nuclear fusion. Nuclear reactions. Nuclear reactions cause changes in the nucleus of atom, which in turn leads to changes in the atom itself. Nuclear reactions convert one element into a completely different element. Suppose if a nucleus interacts with any other particle and then separates without altering the characteristics of the other nuclei, then that process is called as nuclear scattering. Rather than specifying it as nuclear reaction, this does not imply to radioactive decay. Nuclear reactions, their types: inelastic scattering, elastic scattering, transfer reactions, capture reactions. In inelastic scattering, the process takes place when a transfer of energy occurs. It occurs above threshold energy. Elastic scattering, it occurs when there is energy transfer between a particle and intent nuclei. It is the most vital process for slowing down neutrons. In case of an elastic scattering, total kinetic energy of any system is conserved. Transfer reactions. The absorption of particle followed by discharge of one or two particles is referred to as transfer reaction. Capture reactions. When nuclei capture neutral or charged particle followed by discharge of gamma rays, it is termed as capture reactions. Radioactive nuclides are produced by neutron capture reactions. Applications of nuclear energy. Nuclear technology, nuclear medicine. Nuclear technology is used in industries. Agricultural uses of nuclear technology. Environmental uses of nuclear technology. Biological experimentations. Medical diagnosis and treatments. scientific investigations, engineering projects, neutron activation analysis. What is nuclear fission? When the nucleus of an atom splits into lighter nuclei through a nuclear reaction, the process is termed as nuclear fission. This decay can be natural, spontaneous splitting by radioactive decay, or can actually be stimulated in a lab by achieving necessary conditions. The resulting fragments tend to have a combined mass which is less than the original. The missing mass is what is converted into nuclear energy in the above reaction. The process in nuclear physics in which the nucleus of an atom splits into daughter nuclei. Nuclear fusion. Nuclear fusion is a reaction through which two or more light nuclei collide into each other to form a heavy nucleus. This reaction takes place with elements which have a low atomic number, such as hydrogen. It is the opposite of nuclear fission reaction, in which heavy elements diffuse and form lighter elements. Both nuclear fission and fission produce a massive amount of energy. Nuclear fusion in the universe. Every star in the universe, including the Sun, is alive due to nuclear fusion. It is through this process that they produce such a mind-blowing amount of heat and energy. The pressure at the core of any star is tremendously high, and that is where the nuclear fusion reaction takes place. For example, the temperature at the core of the Sun is around 15 million degrees Celsius. At this temperature, coupled with a very high pressure, two isotopes of hydrogen, deuterium, tritium, fuse to form helium and release the massive amount of energy in the form of heat. Around 600 billion tons of hydrogen is converted into helium every second in the Sun. There's a difference between nuclear fusion and fission. The definition of nuclear fusion is a combination of two or more atoms to create one large atom, whereas for nuclear fission, it is exactly the opposite, that is, division of a larger atom into two or more smaller atomic particles. The process is combination, and here it is a breakdown. Occurrences: naturally occurs, does not occur naturally. Products: unless a fission trigger is present, nuclear fusion produces radioactive particles. Always creates radioactive substances as its byproducts, which remain active for hundreds of years. Requirements: two or more nuclei to be near each other in order to create energy for both to stick together. Needs to have a critical mass and a very slow neutron for the splitting to occur. Thank you.